So the last thing we have to cover on Chapter 6 is Section 6.3, talking about cumulative probabilities and a cumulative probability function and cumulative probability tables, which are tables which you will find if you flick to the back of the book just before the answers in the appendix. It's these tables that we're looking at here. Okay. Now, there is also a function on your graphic calculator that will do these calculations for you. My advice is to learn to do this section using the tables, and then you understand kind of the process of it a little bit better, and then once you've done the exercise initially using the tables, you'll probably use the calculator all the time, and by the time you get proficient with the calculator, I would imagine most people will not use the tables by the time it comes to the exam, because it'll be quicker to just type the numbers into the calculator. But to start with, get used to the idea of using the tables. I think it gives you a bit of a better understanding of what's happening. So here's the idea. If we have a random variable which is distributed with a binomial distribution, and let's take an example of something like 10 and a third, okay? So if we've got that, what we'd expect would be the outcomes of that random variable can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And if we represent the probabilities as a sort of bar chart, we'd expect a spike at 3, and a similar sort of spike around 4, and then it would tail off in either direction, and we get this sort of thing. So if you've got a binomial distribution like this, the probability of getting a result of 10 is quite small. The probability of getting a result of 3 is relatively much bigger, so the probability here is the highest. Now, that's what we're picturing. We often want to ask questions like, what's the probability that the random variable takes the value 4? What's the probability of getting a 4 on this experiment? And then we just look at the height of that stick, or we'd calculate it using the formula from the previous section. But we're also interested in questions like, what's the probability of getting 4 or less, or what's the probability of getting more than 6? Okay, so if you frame this in terms of flipping a coin, so this is flipping a coin 10 times, the probability of getting a heads on this coin is 1/3. Then what's the probability of getting 4 heads or fewer than 4 heads? What's the probability of getting more than 6 heads? Okay, so those are the sort of questions that we want to ask. And what we have is we have tables that will answer that question for us. Now, if we go and look at the tables in the back of the book, if you've understood everything so far about binomial, then this should sort of make sense just from looking at this bit of the table. So let's have a look what it says. It says, the tabulated value is the probability that the random variable x takes the value less than or equal to the value little x, and the little x is the value given in the table, where the random variable, capital X, has a binomial distribution with index n and parameter p. So in other words, we have a random variable x, which is distributed with a binomial distribution np, and n and p are given in the table. So let's take an example. Let's look at this number here. This number is n is 5, tells us that there. X is 1, tells us that here. Here are the different values of x. And p is 0.25. Okay? So we've got the probability that this random variable x takes a value less than or equal to 1 when n is 5 and p is 0.25. Okay? This table tells us the probability that random variable x takes the value less than or equal to than whatever it is we want to look up. So if we have, oh, excuse me, it's just started raining for the first time in weeks, and it sounds like there's some thunder outside. So if we have a binomial distribution, x is distributed binomially with, I don't know, 10, well, let's take the same example, 10 and, let's not take a third, let's take 10 and 0.3, pretty similar sort of one. That's our value of n, that's our value of p. If we're interested in the probability that this random variable x takes a value less than or equal to, what did we say before, less than or equal to 4, then what we need to do is go to the tables. We need to find the part of the table where n equals 10, and that's down here, look. We need to find the part of the table where little x equals 4, so that's this row here. And then we need to find that p equals 0.3 part of the table, and p, it tells us along the top. So 0.3 is this column here. Looking down that column, when n equals 10, when x equals 4, I get this number here, 0.8497. 0.8497. and that is the probability that the random variable x takes a value less than or equal to 4. Okay, so that's how these tables work. If you know the n, the p, and the x values, you can look things up in the table. Now, obviously, anything that you've seen like that before, you can imagine the next thing they're going to do. In this case, they're asking for, what the tables will do is they will tell you this if you know n, p, and x. So one sort of question they could ask you would be, they tell you the value of this, and they tell you the value of n and p, and they ask you for the value of the little x, or they tell you the value of this and the little x. And we've got 4 things involved: little x, n, and p, and the probability that the random variable x takes a value less than or equal to 4. The easiest thing is if they tell you these 3 and ask you to find that one. But like any question where there's 4 things involved and they're usually asking you to find this one, they could ask you to work backwards. Okay. The other thing to be aware of here is that we're not always interested in what's the probability of getting a result of 4 or less. Maybe we're interested in a probability of, and there's a little table here, probability of getting more than 5, less than or equal to 3, and all these things. Now, I think the worst thing you could do is try and memorize this table here, okay? Greater than 5 obviously means, probability of getting a result greater than 5 means the random variable strictly greater than 5. No more than 3 means 3 or fewer. So turning this column into this column should be fairly straightforward. Where people make a mistake is that once you've got this, you try and get to this bit straight away. And what my advice would be is from this, you should be able to work these things out using a bit of common sense. So let's have a look at how that would work. Let's have a look again at our table here. Now, if I'm interested in the probability that this random variable takes a value greater than 5, okay? If I'm going to use the tables, well, if one of the probability is greater than 5, what I could do is I could say, well, that is all of these values here, right? 6, 7, 8, 9, and 10. I could work out the probability equals 6 because I've got a formula for that. I could work out the probability that it equals 7 because we've got a formula for that. And same for 8, same for 9, same for 10. So I could do those things and calculate them all. The other thing I could do is I could say the probability being greater than 5, well, I know that all of these probabilities add up to 1. So if I do the probability that x is less than or equal to 5, that would be all of these probabilities here. So if I do 1 minus that, that's going to be the same as this, okay? So the probability that x is greater than 5 is the same as the probability, 1 minus the probability that x is less than or equal to 5. Now this one, I can look up in my tables. Remember, for the table to work, this needs to be a less than or equal to symbol. So I can look that up in the table, do 1 minus the number from the table. That's going to be a lot less work than calculating the probability that the random variable equals 6, probability that the random variable equals 7, probability it equals 8, probability it equals 9, probability equals 10. Finding each of those with the formula and adding those numbers up is going to be a lot quicker to look at one number in the table and then do 1 minus the number that you found. And you can apply the same sort of logic. So let's stick with n equals 10 for the moment. We can, obviously n doesn't have to be 10. But you apply the same principles. So if you're interested in the probability that the random variable is less than or equal to 3, well, that one's straightforward. That's a less than or equal to sign, so you can just look it straight up in the table. Probability that the random variable is greater than or equal to 7, greater than or equal to 7 is these numbers here. So that is 1 minus the probability that the random variable is less than or equal to 6, because the probability of getting 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, all of those things together adds up to 1. So if I'm interested in these ones, I need to do 1 minus the probability of these ones, and that is the probability that's less than or equal to 6. Instead of memorizing each of these results, my advice would be to just draw this kind of a diagram, okay? And we only need a few numbers on there. So the next one in the table, I'm using these examples from the table because they cover all eventualities. But like I say, don't try and memorize where the 1 minuses are. Don't try and memorize when you've got a less than, it turns into a less than or equal to with a number bigger or a number smaller or something like that. Just try and get the idea. So if we want to know the probability that the random variable x is less than 10, strictly less than 10, picture the numbers 8, 9, 10, 11, 12. Strictly less than 10 would be these numbers here, and that's the same as less than or equal to 9, okay? So the probability that the random variable is less than or equal to 9, and that one we can look up in the tables. This one we can't look up in the table because it's got a strictly less than symbol, not a less than or equal to symbol, okay? That's the idea with the cumulative distribution tables. And you'll see in chapter 7 some more reasons that, that they're particularly useful when we start talking about critical regions for hypothesis testing.